Welcome everybody. My name is Jirka Pechanec, and I will be talking about streaming database changes into Kafka and other downstream systems using Debezium project. So, first let's start with the agenda today. So, at first we will discuss what are use cases for change data capture, change data streams. Next, we will go through different ways how to create change data streams and how to connect them to the other systems. Then we will speak about change data capture with Kafka, Kafka broker, and using Kafka Connect framework for connecting databases to the Kafka. And the core of the presentation is speaking about Debezium, which is the project I'm working on, and that is dedicated especially to this topic. And I will sometime near the end I will show you also a demo of the project. I will show you how the changes from the database are streamed. So first of all, what is change data capture? What is it about? Change data capture is mainly about detecting changes in the database, about detecting changes in the data, but not only changes of the data, but also schema. So metadata of the database, and stream them to broker or another storage. Here on this picture, we have an example having a source database that streams changes into Apache Kafka broker, which are then read and synchronized to another database. What are typical use cases for change data capture? I would say there are three different sets of typical use cases. The first one is the one that I usually speak about first because I'm coming from the system integration background, and it's data replication. We can use change data capture for replicating data from one database to another database, but to a database from a different vendor. Yeah? So you are not replicating MySQL to MySQL, but for example MySQL to Postgres. You can stream the data from the database to analytics system like Spark or Flink, and you can do streaming analysis, big data analysis on those data. Or you can feed the data to I would say almost any other system, or you can use it to cooperate with different teams. So you feed data from the database to other teams that then consume them. The next use case, and I would say it's quite popular these days, is microservice architecture. In this case, we are trying to propagate data from storages, from local storages of each microservice to a global bus. So we can then orchestrate the services and react on changes or on events from one service by other service. What is great in this case is that there is no coupling between those services because we are using asynchronous communication or more precisely messaging. This will allow us to have specific storage for each microservice, and this storage or this data store can be optimized or contain optimized view for each service that needs to read data. And using streaming, we are keeping all those data stores in sync. The last case is, I would say, something like supplementary cases. So it's not for primary use, but it helps you with the application infrastructure, keeping in sync. If you have an application that uses database, and for improving the performance, you are putting a cache in front of the database, you can update the cache in front of the database via change data capture, or you can invalidate the cache. So the cache and data store behind are kept again in sync. Another approach, you have data in database and you need to execute full text search. Some of the databases already support full text searching, but it's definitely not that powerful as you might need. So it might be advantageous to stream your data into the system like Elasticsearch or SOAR for supporting full text search over your data. And the last use case is CQRS design pattern. In command query responsibility separation, you have application that receives commands for modifying the data, and those commands are updating models from which or views that serves as a source for read. And again, in this case, we can use change data capture for keeping or for syncing the read models in sync with the commands coming from the application. Okay, so what are the ways how to capture changes? How can we achieve this? How can we capture the changes in the database? There are multiple approaches how to do it. I would say the simplest one are dual writes. So if we are talking about the example of database, cache, and full text search, then with multiple writes, your application will do the write to the database, then will write the update to the cache, and will write the update to the index for full text search. What is the problem? Problem is that all of this is cluttering your business code because it's just ceremony. Yeah, you are just doing all the same, just to different sources. Then you need somehow to think about how to handle failures. Yeah, in these days, it's definitely not popular to use two-phase commits. For such a scenario. So how you would handle a situation when you write data into database, and then there will be a failure when you will write when you try to write data to the cache. So this is something that you need to somehow handle, and again, it's not cheap, and it's definitely complex. And last but not least, again, as two-phase commits are not popular, this approach is definitely prone to race conditions, because as a writer will write the changes to the different stores, it's not guaranteed that the reader will see the changes in the same order as the writes were created. So the reader can see the index updated, but it's possible that the database change is not still visible to it yet. So It might work, this approach might work, but it definitely brings a lot of disadvantages that needs to be handled on developer side. Another approach is polling for changes. So what you will do, you would, let's say, look at the database table and monitor if there are new records arriving, and if yes, then you will just capture a record or select the record and stream the record downstream. Well, it works. It's pretty simple, but there are again problems. First of all, how you detect not that there is a new row, but that the row was updated. So you somehow need to version the records and detect that the version of the record has changed. So you stream it down again. Or how you recognize that something was deleted. In this case, you would need to keep somewhere a list of records in the table, and you would need to react on a record disappearing or missing from your local copy. So this is definitely not feasible. There is also one more option which is not mentioned here, and that's using stored procedures and triggers. Yeah, but we all know disadvantages of triggers and stored procedures, and that's typically performance, and that's a problem of versioning of the code in the databases and keeping it in sync. So it could work, but again, it brings a lot of disadvantages. So how should we capture changes in the right way? Well, that's the way how we are doing it in Debezium, and that's we are monitoring the database. We are monitoring the database log that contains the list of transactions. Effectively, we are behaving like a replica of the source database. So all transactions that are recorded to the database log are processed by changing the data capture system and streamed to the other systems. What if there is a failure? It's not a problem. If a database is not available for a few hours, or if the streaming system is not available for a few hours, it will just cause a delay for streaming the data, but there will be no inconsistencies, because as soon as the streaming system is up or database is up, the database log is read and all the changes are streamed down to the system, so it can be consistently processed. And all of this is completely transparent to the upstream applications, so they are just blissfully writing to the database, and they don't care about, let's say, this magic behind the scenes that streams the changes to the other applications. So I've been talking about database log. What is database log? If you look at this expression closer, from closer view, it's just the way how the database implements durable writes. How it works? Application writes a change to the database. Database records the change into transaction log or replication log, or in case of Oracle it's called redo log, and after that, after some time, it physically updates the tables. So the transaction is recorded in the log, and if the database crashes in between, the changes are replayed from the log file and the tables are updated. And this log file is used also for replication. So for MySQL, this log is called bin log, and the replication works in that way that the changes from the bin log are sent over the wire to the replicas. In case of Postgres, it's so-called write-ahead log. It's again, it's a different name, but the principle is the same. And Postgres contains so-called logical decoders that allows us to hang on write-ahead log and decode the events and translate them into something meaningful, something logical. And in case of MongoDB, it's just the plain op log that is core of MongoDB replication. So we are using those logs for change data capture. As now we have the source of the changes. What are we doing with them? We are going to store the changes to the Apache Kafka broker. Why have we chosen Kafka broker? The Kafka is very well suited for change data capture for these reasons. First of all, every message have a key. So if we are streaming changes from database table, we can associate primary key of the change in the database with a key of the message that is sent to the Kafka. We have guaranteed ordering. So the changes as are written to the transaction log are written in the same order to the Kafka, and they are consumed in the same order by Kafka consumers. There is, of course, certain limitation, and that's the ordering is guaranteed just per partition. If you start partitioning the data, you are, of course, losing the ordering. Also, what is nice feature is that Kafka supports compaction, which means that if we have multiple changes for the same entity in the database, we can configure Kafka to store only the last change to the event. So, to the database row. So if we use Kafka as a storage, by using compaction, we store always the last change or the last value of the database row. And last but not least, Kafka is great in horizontal scaling. So it's not a problem to add or remove, or more precisely, it's not difficult to add multiple instances of Kafka broker in case there is a performance problem. Kafka broker is a storage, but Apache Kafka project is not only broker, but also other components. And for change data capture, we are using Kafka Connect framework. Kafka Connect framework is framework for developing and deploying connectors between data sources or data sinks and Kafka broker. So you can connect, for example, file system, monitor changes, and write the changes or content of the file system to the Kafka topic. Kafka Connect also supports tracking offsets. What is it, tracking offsets? Well, offset in this case is identifier or location of, for example, in the database log, position in the database log that is recorded in the Kafka. So in case of crash, we know from where we should start streaming again. So there is guaranteed that no data are lost. The next one is support for schemas. Connect is sending the messages to the Kafka with associated schema, with associated metadata, so we can easily keep in sync the schema of the table or the changes in the table over the time as the schema of the table evolves. because every record has associated a schema of the table at the time the change was captured. And also Kafka Connect supports quite well clustering. Kafka Connect supports two modes of running. One is standalone, which is just a plain process that runs multiple connectors, or so-called distributed mode, where you can start a cluster of Kafka Connect instances. You register multiple connectors, and the Kafka Connect automatically distributes the connectors between instances of Connect cluster to keep it somehow balanced. So, if we have Kafka Connect, how does look the change data capture topology with it? So, as an example, here we have two databases. One is MySQL, one is Postgres, and we have Apache Kafka broker. So we are putting Kafka Connect in front of the Apache Kafka. So we have a framework that will stream the data or record the data to the Kafka. And again, Kafka Connect behind the Kafka. So something that will read the data from the broker and write it somewhere else. Then we deploy specific connectors to the Kafka Connect on the source side. So in case of Debezium, it's for MySQL, it's Debezium MySQL connector, or for Postgres, Debezium Postgres connector. So we are capturing the changes and writing them to the Kafka broker. And at the end, we have a Kafka Connect that runs Elasticsearch sync connector, so connector that will write data somewhere. And in this case, it means that it will read the topics and will write the changes into Elasticsearch using Elasticsearch connector that is developed and open sourced by Confluent. On the destination side, if you are not, let's say, only Kafka shop, you can use arbitrary application that uses that knows how to communicate with Kafka. So it's just plain simple Kafka Consumer. In this example, you have an Apache camel with Apache with Kafka module, or Eclipse Vertex again with specific support for Kafka, which are reading the changes, receiving the changes from the topics, and they are streaming the changes to downstream system. In this case, it can be legacy enterprise information system. How does change data capture message structure looks like? I've already spoken about having that each message have a key. So the CDC message consists of two parts. It's a key and value. Key is just equivalent of primary key from the table. So the table is analyzed and the primary key is extracted. And the payload is a complex structure that contains multiple parts. First, it's a before part, which contains the data in the row before the change was applied. In case of insert, before is of course null because there was no change, no state before. Next one is after state, so that's how the database row looks like after applying the changes. And the last one is source info, and this is the information, this is the offset or information from the source location. So in our case, it's a position in the bin log. You can see it like a file. So it's MySQL binlog file and position in the file. The format of the message is twofold. It can either be JSON, which is nice because it's human readable, so it's easier. So it's easy to debug the problem. It's unfortunately a little bit verbose, but what is nice that Kafka Connect supports adding schema to the JSON. So you can have either just plain JSON or, as we can see in the example, the one that contains in the first part contains schema, and then it contains the payload. The other option is using Avro binary format or Avro serialization. Avro is quite advantageous because it's very compact. It's way faster to transfer the data over the wire, and also contains or can contain the schema or reference to the schema. If you are using Avro, you need to use Confluence schema registry component, because every message in Avro format has an identifier to the schema that is stored in this schema registry, and during the deserialization of the message, the identifier is taken, and the consumer queries the schema registry, receives the schema, and decodes the message. Well, so now you have a database and you would like to start streaming. What can happen? The problem is that your database can be quite old. So it means that the transaction logs will not be available because they are typically purged after a few hours or days. Debezium is prepared to handle such a situation using so-called initial snapshot. So whenever the connector is registered, it will check if the bin log is available from the start, and if not, it will take the snapshot of tables that we would like to stream, will convert the content of the tables to a stream of insert events and send it downstream. So it effectively prime the downstream systems with already existing data. After the snapshot is completed, we are switching to the log reading, and we are continuing in usual streaming way. So, what connectors does Debezium support? So far, there are 3 connectors already released. That's MySQL, which is the oldest, Postgres, MongoDB. For MongoDB, we are using patch format for the messages. And there are more connectors planned. The first one, or the nearest one, is Oracle. Oracle connector is almost completed. There is a pull request already prepared. Just merge or the final review and merge has to be done. So you can expect the Oracle connector in the next release. There is definitely SQL Server planned to be done in future, and we are now considering other option. Maybe it will be Cassandra, maybe it will be MariaDB, it will be, we don't know yet. Yeah? Okay, so DB2, to be honest, we have been a little bit unsure about it, but there were definitely few requests from the community recently, so it's possible that DB2 will get on the list too. So no promises, but there are definitely requests for it. So we were also a little bit surprised about it. Debezium connectors. We are trying to to keep the connectors as similar as possible. So we are trying to use the common format between the connectors. So the consumer, if the consumer processes a message, it shouldn't be necessary to consider from which connector it arrives. We are providing a common set of options for all those connectors. Typical example are filters. So that's whitelist and blacklist filtering that allows you to define which tables you want to stream and which tables you want to ignore. And of course, it's the snapshotting mode. It's the snapshotting I was talking before. So either take snapshot or doesn't take, or there are also multiple specific snapshotting modes. That's discussed in documentation. Also, we are supporting monitoring of the connector states via JMX. Typical metrics we are providing is the snapshot progress. So how many tables have already been snapshot? How far do we lag behind the master? So you can monitor this value and to see if Debezium is keeping in sync or if it's seriously lagging, and of course the information about last event. How the connectors are operated. Kafka Connect provides provides a REST API that allows you to register the connector, to set it up, to manage the life cycle of the connector. So stop it, resume it, remove it, restart it again, and again also supports a subset of monitoring values. What is interesting in the connectors is that whenever one of the components in the system dies, it will not create any inconsistency, but it will just create a delay in delivering the events. So now it's a time for a demo. So I have a plain Java EE application that uses MySQL as data store, and we will try to stream the changes from the application to the Kafka broker. So this is the application that allows you to track hikes. So let's try to create a new hike. So I have arrived from Brno, and I am in Krakow. So there is a new hike recorded in the system. And now let's look how this should work. First of all, we will start up Debezium. We are using Docker Compose to start up all components necessary by Debezium. In our case, it's Zookeeper for Kafka, Kafka itself, and Kafka Connect instance. We have already MySQL instance running. So if we run Docker PS, we see multiple containers already running. So first of all, we will register MySQL connector to start the streaming. So the registration request has succeeded. We can see that's a MySQL connector. We are connecting to MySQL database with these credentials, and we are connecting to the Kafka server, Kafka on the port 1992. So we are probably connected and started to stream something. So let's look at one of the topics created by the system. For this demo purposes, I'm using Avro serialization, so I'm using schema registry. So as you can see, multiple events has been created. So these were first 4, original one. The last one is the one I have created. So the events from the database were streamed to the Kafka topic. Let's create a new hike. So now let's suppose I'm coming from Prague again to the Krakow. And if you look here, we can see that a new event has arrived immediately to the Kafka topic. Let's suppose that we have made a mistake. So we update the Prague from Prague to Praha. And if you look into the changes, we can see it's ID 6, and the event is more complex. It contains the old value Prague and Krakow, and new values Praha and Krakow again. Yeah? So this is how the update works. Now let's remove the hike because we have cancelled it. So let's remove it. And now we can see that there are 2 new events. First one is this one. It contains the original content, and the operation is D, so delete. So we have removed the record, and then there is one more message, and that's it contains its null. This is so-called tombstone event or tombstone message. That means that in case of compaction, this is a sign that during the compaction, all events with primary key ID 6 should be removed from the Kafka broker because it was removed. So this is Kafka's Kafka tombstone functionality. Okay, so now as I have mentioned that we are using schema registry. So let's look into schema registry. I have queried the schema registry for schema of the message that we are sending. So you can see there is completely described schema. So for before there is ID type long, destination start of type string, and so on and so on. So we can see that every event has a schema associated and stored inside the schema registry. So let's continue with the presentation. So the next topic is message transformations. Kafka Connect supports a limited way how to transform or modify messages via so-called single message transform, SMT. It's the typical use cases is extracting part of the message and replacing the original message with this part, or converting the message from one format to another format, or route the message to a different topic. Yeah? Kafka has out of the box, I think 8 or 10 SMTs, which can be applied either on the source side, so it's applied on the message before it's stored in the Kafka broker, or on the sync side, so the SMT is then applied after the message was read from the broker and the consumer sees the converted message. Debezium provides 2 or technically 3 different SMTs out of the box. The first one is a logical table router. This SMT allows you to route event to arbitrary named topic. Why do we need it? This originates as a community request for cases if you are using sharded data. So let's suppose that you have a huge set of the data that you have sharded across multiple tables. Without this logical table router, every record will end up in different topic according to the shard, because each table has its own topic. If you apply logical table router, you can arrange a setup that all those shards or all those events from the tables that are different shards of the data set will end up in the same topic, which is usually what you want to achieve, because they belong to the same data set. The other two SMTs are so-called event flattening SMTs. Again, why do we need them? I have shown you an example of how the message looks like. Yeah? That it's complex data structure that contains the state before the change and after the change. This is great because you have all information available. It's always better to provide more information than less. The problem is that the sync connectors, downstream sync connectors, are not able to work with such a format. So we are providing SMT that allows you to extract only the after part of the message, so effectively flatten it and convert it to the format that is understood by all sync connectors. So in this case, you apply the SMT and you can stream the event from the Debezium source to JDBC sync connector or Elasticsearch sync connector. So let's look how it works. So I have started not only MySQL database but also Postgres database that would act as a target for our changes. So first of all, let's look into the database. So I tried to query this table that should contain the changes from the topic, and the table doesn't exist. Why? Because we haven't registered Postgres sync connector yet. So let's try registering the sync connector. So the connector has been registered, and if we try again the select, you can see that we have received the changes that were already in the Kafka. So let's try to create a new hike again. So let's say from Brno to Katowice. And now let's look into the Postgres table. And you can see that the table contains the change that I have created in user interface and was streamed down to the Postgres. Just for maybe you have noticed that there is a change that we have already removed, the Krakow Praha. This is intentional because the data are in the topic. Unfortunately, JDBC sync connector is not able to, it doesn't support deleting the changes. So it will contain the data, all data that appeared in the topic. Let's try to update. So we will change Brno to Brno 2. So albeit deletes are not supported, updates are supported, so we can see that Postgres was updated and is now in sync with the source MySQL database. And as we have still a couple of minutes, I have one more demo prepared to you, and that's showing you how we can use another application to consume events from the topic. So in this case, we are using Vertex application. Let me check. I need to start it. I need to start it as a daemon. Now let's look at the localhost 5000. Yes. So we have connected to the Vertex, and we are using WebSocket to receive events from the Kafka and stream them to the Vertex. So let's try to create a new. Sorry, I forgot to register one more connector because we are using a JSON for this case. So JSON format. So I have registered a connector, and you can see that immediately WebSocket has, or the events from the database were streamed via WebSocket to the application web page. Okay, so how can you try Debezium yourself? We are extensively using Docker, so we have Docker images for all components used by Debezium. We have extensive tutorial available that you can try and step by step reproduce what I have shown you right now. We have also a set of Docker Compose files that allows you to start the environment in the same way as I have started it now. And of course, we are also OpenShift ready. So you can use Streamzy open source project to deploy Kafka on the OpenShift, and then deploy Debezium to the to the Connect cluster that is also deployed to the OpenShift via Streamzy. If you are not familiar with OpenShift, or you don't know how to start it locally, you can go to the learn-OpenShift.com that contains a tutorial from our site that again interactively starts on the remote site an OpenShift environment, and you deploy the components, Debezium components, and you can try it for yourself. So, what are the plans for the future? So, I would say 1 or 2 weeks away is release of Debezium 0.8. This one will be based on Kafka 1.1. And the biggest changes will be the Oracle connector I have mentioned, and it will also contain support for a reactive embedded version of Debezium. The next, or the further version, 0x, will contain a new MySQL parser. We are right now using handmade MySQL parser for parsing schema changes from MySQL. Now we have a pull request for MySQL parser using Antler. Of course, there will be more connectors. We will probably add a support for Infinispan as a source and as a sink also. So for the case of cache synchronization use case. And for Debezium 1.x, probably it's still far away, but I would say the major change or major news will be event support for event aggregation. Right now, the events from different entities are shared, are sent as a separate changes. So we would like to provide a way for you how to combine them together. So, summary. What is Debezium? Debezium brings change data capture for now 3 or 4 databases that you can use. We are working reliably in case of failures and transparently sending data changes via Kafka broker to consumers downstreams. Our project, as everything in Red Hat, is of course open source. It's Apache licensed, and we are very glad for any contribution that arrives. Not only the code, but also improving documentation and everything. So these are resources. Go to our website, look at the source code. We have also a discussion group and Twitter. And that's all. So thanks a lot for your attention. Are there any questions, please? Yes?
Is it possible to reduce the amount of data
So the question is it possible to reduce the size of the message? Yes, it is possible. I have mentioned the filters, and I have mentioned just filtering the tables. But there are also filters for filtering columns of the specific table. So you can say, I'm interested only in monitoring those 2 columns, or I'm not interested in monitoring those columns. Or you can write your own SMT and apply it on the source connector, and this will allow you also to reduce or modify the size of the message. Any other question? Okay, so I'm not sure if it's good sign or bad sign, but anyway, thanks a lot for your attention, and I hope you enjoyed this one presentation and that you will enjoy the rest of the conference. So thanks again.